Good afternoon. Thanks for the opportunity, organisers, to speak here. What I want to, as an aim of this talk, is to impress upon you the importance of soil moisture characteristics. They're critical pieces of information that we need as soil scientists, and they're basically expressing the relationship between the amount of water in the soil and the tension with which that water is held in the soil. And I just want to go through how we get these measurements in the lab. How many here have actually done a soil moisture characteristic? Yeah, in the good old days, you know, you all would have done it. But it is really important information to get, because you actually understand how the soil's behaving in the field when you bring it back to the lab and put these measurements through it. So this is basically how we do. So here's your core, and that's where you measure your bulk density, your volumetric moisture content. And what you can see is that what we're doing is we're draining this soil by increasing the negative potential on the soil, that distance h. So we start off with that distance h being 0, the core saturated, which is taking it out of the field, wet it up to saturation. We're gradually increasing that tension on the soil by increasing h from 0 up to, we can't quite get it in the lab up to oven dry, but we can get it up to potentials equivalent using a range of equipment up to about 15,000 centimetres of water. And this is just picking up the concepts that Jason's so beautifully described to us about how water's held in the soil. And here's our soil, his sponge in the bath, and I knew Nick too, so I can imagine what a horrific feeling that was, thinking of Nick. And so here's our sponge, and then as we let the water drain out, we are at the equivalent of field capacity. It's when soils have been wet up by rain or irrigation, you go back a few hours later, a day later, and they've still got quite a bit of water in them, you know, 20, 25, 30%, and then that happens quite quickly. And then permanent wilting point is reached after the soil starts to evaporate moisture from the surface and plant roots start to extract water. And we reach this stage called permanent wilting point down here. So the water between the field capacity and the wilting point is the water that plants depend on. And that's really important. If you're an agronomist, you want to know that sort of information. So what does it look like graphically? Here's just two examples, and I want to thank, is David McKenzie in the audience? Because I'm using some of your fantastic diagrams out of your handbook for horticulture. But this shows a really nice, in a nice way, how you get differences between these different partitionings of water between the gravitational water. So you can see in a clay soil, there's not much gravitational water compared with a sandy soil. The plant available water is a lot more in a clay soil, and the non-available water is higher in a clay soil because of those cohesion forces that Jason described between the lots of clay, lots of water being held in tiny pores. So you actually have a clay soil quite a non-available water content. So different soils have different capacities for these gravitational water, plant available water and non-available water. And when we do that in the lab and we plot these results out, and what we've got here is on the y-axis, we've got the volumetric moisture content against that value H, the suction that we put onto the soil. So we've brought our soil cores in, saturated them, and you can see the different characteristics that soils have. You know, this is really important information. I always say to my students, if you were going to grow a crop in one of these soils, how much have I got left?
3 minutes.
3 minutes. Which one would you have? And the obvious answer is the one that's got the biggest difference between wilting point and fill capacity. And you can see it's not very good for a sand, so I'd probably go for somewhere between a clay and a clay loam if I wanted the ideal soil, just considering the amount of available water. So really important information to get this. Moisture characteristics are critical in any studies of soil-water relationships and choices about how you're going to grow crops. I've put this up to show you that you can get hysteresis. So here we've got a moisture characteristic curve. The usual way you do it is you do a drying curve. You would have wet your soils up and measured the moisture content at each of those suctions. However, you've got to be careful, particularly for clay soils. If you do the reverse, if you start to wet it up again, you don't get the same curve. You get hysteresis. Things differ on the way up compared with the way down. So if we take what this means, if we look at a value, 10 kilopascals fill capacity, we see that on the wetting curve we've actually got less volumetric moisture content than we did on the way down. And the way I always think of that is in going to very dry conditions, we've got a clay soil and we've got our clay tectoids, clay packets. As they dry out, they tend to collapse down. So as we had quite open structures in the drying curve, when we get to really dry conditions, even air dry, a lot of these structures collapse and they don't come back up together to nice structures again on the wetting side. So we get a different shape. So you've got to be really careful about these effects with soils because they can undergo changes in this drying process. Okay, we've got some cotton agronomists in the audience, yes? Cotton people? Maybe not. Okay. The important thing that this diagram shows is that, as I've said, this is the amount of available water. If you've got a moisture characteristic data, you can work out the amount of water you've got in your profile down to a metre. That's really useful to know. And as you can see, it varies from 50 millimetres for a sand up to a good clay. Self-mulching clay, you can see 4 times as much water. So, you know, where would you grow a crop knowing nothing else? You'd go for a clay. But, so that's the first important thing to get out of that diagram. The second important thing to notice is that it's not constant, right? You can compact these soils. If you do the wrong thing in your management, that's why I was hoping we'd have some cotton agronomists here. David knows enough about that. He did his PhD on it. But right, David, you can really change the structure and you're doing things to the pores that aren't allowing you to get the same amount of water, available water into those soils. So our management of soils is critical. We can change this very important property of water holding capacity if we don't manage them correctly, and compaction is one of the big problems in the cotton industry. Yep, I'll get there. There's going to be a session this afternoon. How many people have collected moisture characteristic data and tried to model it? Okay, good, yeah. That's great. The thing is, most of your moisture characteristic data, as you can see, follows a sigmoid-shaped curve. And it's a lot of people spend time trying to model their moisture characteristic data to get values out of it, like these parameters. So I've been doing quite a bit of work with a colleague just looking at various, and the most commonly used equation is the Van Genuken equation. I've been doing quite a bit of work with a colleague looking at different data sets, trying to find out when you can and when you can't use the Van Genuken model to model them. Okay, so if you've had nothing else stressed upon you this afternoon, I think moisture characteristics are so important. It's like if you measure dust, which is my other crime, you shouldn't measure dust without doing particle size analysis. You shouldn't be measuring soil water without a knowledge and using moisture characteristics. And we'll be talking in the session this afternoon, is that correct, about how we might model some of this data. Okay.